So, let's pick up with what the last little bit of stuff we need to deal with in terms of musculoskeletal, looking at muscle growth through the age and regulation of growth based off of hormone signals. The key hormones that are going to regulate muscle growth are the same key hormones that are going to regulate bone growth. This includes testosterone, growth hormone, IGF and MGF, insulin and adipokines. All of these hormones here are going to function through regulation of key genetic regulators. There is one key genetic regulator that limits the total amount of muscle growth that occurs during development, and that's a genetic regulator or a gene known as myostatin. There are genes that are responsible for hypertrophication, and that includes MyoD, myogenin, myFBOX, and MRF. There are a couple of genes that are going to be responsible for regulation of the mitochondrial issue and the conversion of the two X's toward the two A's. And those are what are referred to as MIFs, M-I-Fs. The MIFs are an acronym for muscle ischemic factor. So, as I ask the tissue to do more aerobic metabolism than what it's able to do, it starts to develop metabolites within the muscle that signal hypoxia or ischemia within the tissue. That MIF triggers within the muscle tissue itself mitochondrial biogenesis, the making of new what? Not cells, mitochondrial biogenesis, the making of new what? Mitochondria. As well as a change in enzymes, so that the muscle tissue itself will be able to do more aerobic metabolism. Along with that, it will also trigger the production of myoglobin, which is the iron-bearing molecule to hold on to oxygen within the tissue itself. So let's take a look at what these genes and what this genetic regulation is going to do in terms of growth and development for the muscle. When we have development, the muscle fiber itself develops through a fusion of cells as opposed to mitotic division of cells. It develops through tubules that form elongated cells. Once those elongated cells have completely formed, the cells do not undergo mitosis. There is no new cell division. All greater amount of tissue, hypertrophication, comes through the integration of what are referred to as satellite cells. Satellite cells are stem muscle cells to areas where muscle tissue has been damaged due to overload. They then integrate themselves into the muscle cell itself and allow the muscle cell to hypertrophy, become larger. And we need the muscle cell to become larger because the larger cross-sectional area, the more what the muscle is able to produce. Strength. Remember, it's not force, it's strength. There used to be an idea that we could actually get new muscle, where the muscle cell will actually divide. That term is referred to as hyperplasia. Hyperplasia is found in lower mammals, but not so much in upper primates. However, if I take a whole bunch of stuff and electrocute the muscles to induce maximal volitional contractions, I can actually induce some hyperplasia. During growth spells, there can be some hyperplasia. However, the amount of hyperplasia is very minimal in humans, with the exception of people who have a genetic mutation. The myostatin gene turns off the amount of muscle cells, fibers that are actually there. If I have a genetic mutation where the myostatin is no longer functional, I will continue to make myotubules, muscle fibers, and so I can no longer make them. the stem cells have been completely exhausted. So, in normal people, what ends up happening is that we have our precursor muscle cell. It gets stimulated by MyoD and MyF, or MyF box, forming myoblasts. These myoblasts undergo a proliferation from myogen and myostatin. What they do is that they start to proliferate, but they don't become too numerous. As they start to proliferate, they start to differentiate. The way in which they differentiate is that they start to fuse themselves together. Any of these cells out here, these precursor and these myoblasts, that don't get integrated into the myotubules or the fibers themselves, become satellite cells. And they basically sit there as dormant cells, stem cells, until they are stimulated. And they're principally stimulated by two key factors. The two key factors that stimulate them: androgen or testosterone, depending upon gender, and mechanical growth factor. Testosterone or androgen, once again, depends upon which gender, because adrenal androgens, DHEAS, which is the female's principal precursor for testosterone, and male testosterone will stimulate these dormant myoblasts to integrate themselves into the myotubules. And mechanical growth factor will do the same thing. Mechanical growth factor is a paracrine signal. It's a signal that comes from the muscle tissue itself and the surrounding muscle tissue that says, hey, a lot of damage has gone on. We need more nuclei because we have to get bigger. In normal people, we stop. And we're limited to the total number of myotubules we have at the terminus of juvenile development, puberty. Once pubertal growth starts, we've terminated the total maximum amount of myotubules we can form. At that point in time, any growth in the muscle is due strictly to hypertrophication. The muscle fiber is getting wider. However, if I happen to have an issue where I have a genetic mutation where myostatin is no longer present, what ends up happening is I don't get this signal here to stop the proliferation. So what ends up happening is that I get my differentiation to the myoblast form. Instead of these myoblasts, some forming dormant stem cells, others forming the myotubules, they all form what? Myotubules. And so what ends up happening is we continually form myotubules throughout development. And what ends up happening is we end up getting excessive hypertrophication of the tissue due to hyperplasia. We get more tissue simply because there's more cells there, as opposed to the muscle cells becoming larger themselves. So here is normal. Here is a myostatin inhibited rat. This here is what's referred to as the Belgian blue bull. The Belgian blue bulls were bred specifically for not having myostatin. Here is a baby with a myostatin deficiency. There have been a couple of cases where they've actually had it with myostatin negative. There are a number of people who are myostatin negative carriers, which means that they can pass on the genetic mutation for the myostatin. People who have myostatin issues tend to have very large muscle, but the large muscle will not hypertrophy. So even though it looks like this guy has a really large muscles, he doesn't have really large muscles, he just has a whole bunch of what? Muscle cells. But the muscle cells themselves are not very big because there's only so much room that that muscle can take up. The problem with this myostatin issue is that it leads to other physical and physiological problems for the organism, in particular cardiovascular issues. Because the myostatin doesn't just work on skeletal muscle, it also plays a role in cardiac muscle. And it plays a role in cardiac muscle combined with a secondary muscle gene known as actin, ACTN. And there's 3 different versions of actin, and the one that leads to people being really good sprinters is referred to as the actin 3A. The problem with actin 3A is it also predisposes the individual to left ventricular hypertrophication, where the left ventricle, the muscle becomes really, really large, the volume within the left ventricle becomes really, really small, and those people tend to suffer from what's referred to as athlete heart death or sudden cardiac arrest.
Is that actin the same that's in the...
No, it's the gene. ACTN is the gene, so we call it actin.
ACTN?
Yep.
Oh, okay.
ACTN, it actually, okay. The actin 3 codes for myosin, but the gene we call it is the ACTN gene. So all genes get acronyms to them.
Yeah.
So like the myF is a myosin fiber gene. That's what the myF stands for. So if we look at this in terms of what they did, so here is the control rat. Everything's normal. This here is where they inhibit the ACT gene that regulates the RB factor. The RB factor is the factor that's going to initiate myotubule formation. Here, they applied a follistin, which inhibits this guy here. So, here, it looks like he has a whole bunch of hypertrophication where the muscle has gotten really, really large. But this is strictly due to excessive numbers of actual myofibrils. More muscle fibers, more muscle cells. If we were to stimulate these muscles in order to get them to contract more often, we would not get a hypertrophication. Additionally, even though this looks like it had like a very, really strong muscle, if we were to actually test the strength of the muscle would be very, very weak because each of the strands are very, very small.
So the bull that you saw was actually
so this bull is not as strong as like a Brahma. A Brahma bull does not have this level of muscle angulation, but the Brahma bull is much stronger than the Belgian blue bull. The problem is that they breed the Belgian blue bull strictly for meat because this guy has a lot more meat within the muscle simply because there's more muscle cells there. So when we look at these adaptations, we basically look at it in two ways. We look at it based on a hypertrophication or an atrophication adaptation. Both hypertrophication and adaptation have to do with hormone signals. Hypertrophication is where the muscle belly itself increases in diameter. In order to get true kinetic hypertrophication, the muscle belly itself gets broader in cross-sectional area because each muscle fiber gets broader in cross-sectional area. Atrophy is the opposite of hypertrophication, where as I no longer load the muscle, I don't have to keep the amount of strength in the muscle, and so what ends up happening is that the muscle slowly starts to reduce its cross-sectional area. The movement from an atrophied to hypertrophied state, some people mistakenly refer to as muscle tone, but muscle tone is simply the set, stable level of muscle contraction within the muscle itself. During growth phases, particularly within the prepubescent, the juvenile leading to adolescent phase, we can get some hyperplasia. However, hyperplasia is very minimal due to the myostatin regulation. Once we get through puberty, all growth that we see within the muscle is purely due to hypertrophication or atrophication. Hypertrophication and atrophication are dependent upon stimulating satellite cells to become active. When the satellite cells become active, what they do is that they provide the muscle fiber with an additional myonuclear domain. In which this occurs is through a sequential event where, once again, I have what's referred to as an acute resistant exertion. In this case here, exercise. So, I have to pick up something. that picking up something causes a change in transcriptional factors, factors that are going to regulate RNA. There's the hormonal response, there's the stress response, damage to the tissue itself, there's response to excessive amounts of calcium being released from the sarcoplasmic reticulum. So, every time I have an excitation-contraction couple, calcium will interact with troponin, but calcium will also interact with other enzymes within the muscle itself. It's not just going just to troponin. Otherwise, we wouldn't have to have as much calcium being released. Calcium interacts with a whole bunch of hormones. Interacting with some hormones will activate transcription factors. Things that go to the nucleus and say, hey, we need to go from DNA to RNA, and RNA into what? RNA into? DNA goes to RNA, RNA goes to? Well, interact with the ribosome. Proteins. So, we say, okay, I need more proteins. These factors here then go to the translational factors at the ribosome. So we increase our rRNA components. We increase the amino acids that become available to the muscle cell. This increase of amino acid availability is referred to as nitrogen balance. If I have a positive nitrogen balance, meaning I have components that will allow me to have amino acids, then I can go to the next step. If I don't have that, I cannot go to the next step. In order to get to this here, I have to meet my protein intake requirement. Protein intake requirement for most individuals, 1.8 to 2.2 grams per kilogram of body mass is sufficient. 1.8 to 2.2 grams per kilogram of body mass. You do not get any benefit above 2.2, regardless of what the meatheads tell you at the gym or what the people at the health food stores are trying to sell you. Because all they're trying to do is sell you something.
So they need protein intake.
1.8 to 2.2 grams per kilogram. If you go above 2.2, you get no benefit.
Okay.
You have no additional benefit going above 2.2 unless you are hypocaloric, calorically restricted in your diet. If I have the availability of the amino acids, then I can start having protein accretion, making proteins. I'm going to make myosin, I'm going to make actin, I'm going to make titin, I'm going to make collagen, I'm going to make elastin, I'm going to make dystrophin. I'm going to make all of the proteins that are necessary for the muscle to be functional. The conversion from this step here to the next step is all about exposure to a couple of key hormones. In particular, growth hormone and androgens, whether it's adrenal androgen or testosterone. And that only comes into play once I have chronic exposure to the stimulus. So, this step here is all about meeting that acute demand. So, I have to pick up something. As I pick up something, the muscle itself starts to tear, starts to have microtrauma in it. To repair the microtrauma, I stop here. But now I have to pick up that same object multiple times, your book bag. The first time you pick up your book bag with all your books, it's extremely heavy. I learned how to recruit the muscle a little bit better, but I still have to get enough protein there so that I have enough muscle to have enough strength to resist whatever that book bag weight happens to be. Now, I have to start activating satellite cells. I have to start activating satellite cells because the muscle cell itself is becoming too large. The muscle itself is becoming too large. I have too much surface area for the volume of the muscle cell. So, the hormones now, androgen, growth hormone, mechanical growth factor, are going to activate satellite cells. Those satellite cells are going to integrate themselves, forming what's known as a myonuclear domain. Once I get the myonuclear domain, then the skeletal muscle itself will undergo hypertrophication, will actually become larger. This last two steps here are all hormonally regulated. In terms of the integration, what ends up happening is we end up having some sort of resistance activation. The resistance activation causes muscle contraction. Muscle contraction causes the internal response to cause an increased protein synthesis. We get hormone response if we have it for prolonged periods of time. That causes a change in what's going on within the nucleus. That change within the nucleus will cause more proteins to be synthesized and put into the muscle. We will also get activation of the dormant myoblasts, the satellite cells. This last step here does not take place until this becomes so much that the muscle cell itself has become too large. And what ends up happening is that we go from having a muscle cell that looks like this to a muscle cell that looks like this. As we integrate new satellite cells, the satellite cells undergo what's known as a proliferation phase, just like what we saw with the myostatin picture. So, as they get activated, they split. They divide, they proliferate. One or two will get embedded, the rest of them will stay as satellite cells. This will go on until it has reached its telomere max.
Spell that, please.
Telo, T-E-L. O. Mere. M-E-R. The telomere is the end chunk on the genes that says time to stop dividing. That sets what's referred to as the genetic maximum for hypertrophication. The problem is that every time I undergo this process here, I have to spend some time reteaching the muscle how to contract. The only way to get this process to occur is to generate enough damage within the tissue to stimulate growth. This is what leads to the muscle soreness that you experience following any type of resistance activity. Once again, it doesn't mean having to go to the gym and lift weights. If anybody's ever had to hew a tree or do any type of yard work, you can get the same type of muscle damage doing that type of exertion. For any new moms carrying babies around, can do the same thing. We can only get this part here as long as we have the positive nitrogen balance. Anything that is left following the signal for replication goes into sequestration and waits for the next stimulus. And so what ends up happening is that we go from activation to proliferation to differentiation and integration. So we start from having 4 pi wedges to now having what? 8 pi wedges. Okay, the volume of each pi wedge is the same. The volume of each mononuclear domain in the unhypertrophied and hypertrophied state are the same. So if we put this nucleus can only control so much volume. Once that volume has become maximized, I now need a new what? Now I now need a new nucleus. The regulation of whether or not I integrate into the fiber or generate a new fiber is whether or not I have an active, or actually more importantly, inactive myostatin in an activated myo-D gene. The way in which fibers hypertrophy is based off of what's referred to as the overload principle. Simply put, I'm not going to hypertrophy unless I add at least 10% beyond what the muscle is capable of doing. So if my muscle is capable of doing 100 kilos, I would have to do 100 and what? 10 to stimulate hypertrophication. If my muscle is able to do 200 kilos, I would have to add 20. 10% of 200 is 20. And so on and so forth. It's all about percent. It's not about total actual load. It's always about that extra 10%. Because that extra 10% minimizes the amount of concentric motion I can do and minimizes the amount of time I can keep an isometric contraction. Which means that if I'm trying to move something, and I can only move it this far, I can only keep it here so long before my hands automatically start what? Lowering down. But I want the weight to come up, so am I going to allow the weight to just drop? No, I'm going to slowly allow it to come back down in an eccentrically controlled contraction. That eccentric controlled contraction causes more and more and more and more and more microtrauma within the tissue. The more microtrauma I get to the tissue, the more hypertrophication I'm going to stimulate, just like with bones. The more microtrauma I get to the bone, the stronger the bone becomes. It's all about said principle for both the muscle and the bone. We do not get hyperplasia in this case, with the exception of reports coming from the Soviet Union in the late 70s to early 80s. And for anybody who doesn't know their history about this, this is kind of sketchy in terms of what they did. All of their Olympic athletes were on doping cocktails that would make Lance Armstrong jealous. And not only were they on doping cocktails, they were stuck to portable electrical muscle stimulation and fixed muscle stimulation. The portable ones are little boxes that are controlled by 9-volt batteries. But they didn't just put surface electrodes, they actually embedded the electrodes into the muscle themselves. And then they used high voltage ones coming from a plug in the wall. And by doing that, they were able to maximize the genetic potential for the muscle. Once that genetic potential got reached, connective tissue started to embed itself within the muscle fibers. And so what ended up happening is you have what was referred to as pseudo-hyperplasia. It looked like hyperplasia, but the muscle cell and the muscle fiber didn't actually split into two. Connective tissue grew into the muscle fiber itself, because otherwise the muscle fiber would have completely split.
So the ads you see on TV where the person's laying on the couch and they got the waistband on and their stomach's going like this.
Yeah, but the problem with that is that the people they're selling it to don't have too much subcutaneous adipose tissue for the electrical signal to get through, and so what ends up happening is they're basically burning the adipose tissue for the people who are actually buying it. The surface electrodes that they do are inducing muscle contraction by stimulating the motor end plates.
So it works, but not too.
Well, it works, but the problem is that the way in which they sell it on TV is not the way it was designed to work, because the electrical muscle stimulation units are there to reteach you how to contract the muscle.
Doesn't feel that great either.
Well, it depends on who sets it up and where they set it up. It typically takes somewhere in the neighborhood of 8 weeks before you actually will see macrostructural growth. That macrostructural growth will continue on that same concurrent path based off of the continuum of the SEB principle, where it takes upwards of 8 weeks every time I try to induce a growth. However, each time I start growing, I have to step all the way back to the beginning of the SEB principle and start with change of motor recruitment and work my way through. So what happens is I start with my normal resting muscle. I then have progressive overload over time. I now have my hypertrophied muscle, with the key being each one of these pi wedges are the same volume as the original. So if my diameter increases twofold, I'm going to have a twice increase in the number of mononucleotidames. If I increase threefold, I'm going to have 3 times the number of mononucleotidames.
Will that increase always happen, you'll go from 4 to 8 and then you double it, or would it go from 4 to 5 to 6?
It all depends on how much overload you have and how chronic the overload happens to be. It's just easier just to represent as that. What ends up happening is that when I can get maximal contraction, I can get all of the muscle firing at the same time. The longer I contract, and the more often I contract, particularly to the maximal contraction that I can possibly do. So, when I ask you to do the hand grip dynamometer and you are to squeeze as hard as you possibly can, you are trying to get to what's referred to as your peak maximal volitional contraction. That is how hard I can actually cognitively get my flexors of my forearm, my antebrachial flexors, to actually contract. Can I get you to contract harder? Yes. With more force? Yes. But I'd have to do what to the muscle? I have to put electrodes on there and actually stimulate the muscle to contract it further. Because most people will cognitively stop themselves from getting all the way to recruitment of the entire muscle.
Will you get the same force if you squeeze fast or if you squeeze slow?
We get the same force.
Or
You'll get this. You will get this.
Let's
No,
just say, will you
maximal.
say maximum volume?
Maximal volitional contraction means that I have contracted the entire muscle to the maximum amount I can do cognitively. It's not about speed. It's about how much of the muscle is actually contracted. The more often I do it, I'm going to get hypertrophication, and I get hypertrophication principally in the type 2 fibers. I do not see very much hypertrophication in type 1s, simply because the type 1s have to stay very, very close to the capillaries. Because I have to have diffusion of gases. The bigger the distance I have to diffuse, the less diffusion I have. In terms of the type 2 conversions, the type 2X's will convert to type 2A's over time. It has to do with the exposure to the MIFs, causing them to become oxidative in capacity. So what ends up happening is that we say with training, the 2A fibers increase. They increase in size, and then they increase in number. The reason why I say they increase in number is because the 2X's and the 2XC's and the 2BX's and the 2AC's start slowly becoming 2A's. If I stop using the muscle, all of these converted 2A's slowly start working back to X's, which means that the muscle can do a very, very quick and very, very powerful contraction, but can it produce any type of work? No. This is what happens to the older people. This is what happens to people who have neurological injuries. Older people, once they initiate a motion, they can very quickly do the motion. The problem is, if they have to go any distance, it becomes problematic to them, because they can contract very quickly, but can they contract with enough time to get true motion to occur? And the answer is no. People who have neurological deficits, spinal cord injuries, upper motor neuron injuries, because these two fibers are not being recruited, they lose their oxidative capacity. If 2's lose oxidative capacity, they become X's. If 2's gain oxidative capacities, they become A's. The A's and the X's will move along a continuum between them through what is referred to as plasticity, which means that as they're being used, they will behave more A-ish. As they're not being used, they will behave more what? X-ish. But we never from 1s to 2s and 2s to 1s. The 1s will increase their mitochondrial density and will increase their oxidative capacity to work forever. The more often the 1s are being recruited, and every time I do a muscle contraction, what muscle type is being recruited? The type 1s. The more often I ask a muscle to contract, the more work capacity that muscle has, because the 1s are undergoing their plastic adaptation.
They'll increase their mitochondrial-like numbers.
Yep, mitochondrial density goes way up, capillary density goes way up. The more often that muscle is recruited, the redder that muscle becomes.